Hi, we present our work Discontinuity-aware Normal Integration for generic central camera models. Our work focuses on surface normal integration, where given an input normal map and camera intrinsics, the goal is to reconstruct a surface in the form of a depth map. Over the years, multiple solutions have been proposed. However, a number of challenges remain. The first challenge is modeling depth discontinuities, which naturally arise due to self-occlusions. Recent approaches have proposed techniques to take discontinuities into account. However, they model their magnitude only implicitly. Additionally, all proposed methods are designed for orthographic or ideal pinhole cameras, which limits their applicability to more general real-world cameras. In this work, we propose a novel formulation that models discontinuities explicitly, can handle generic central cameras, that is, cameras with a center of projection, and also more accurately describes the ground truth relation between normals and depth. The majority of the previous formulations for surface normal integration are based on orthogonality constraints defined in image space. These result in a set of partial differential equations from which solutions can be derived for orthographic and pinhole cameras. We instead propose a formulation derived from slightly different assumptions. First, we introduce subpixel modeling by considering for each set of neighboring pixels A and B a subpixel M that interpolates between them. We then propose to parameterize the surface points through ray direction vectors. Looking at the problem in 3D, we can define the following equations for the 3D points PA and PB associated to pixels A and B, based on the definition of ray direction vectors. The same principle can be used for the coordinates of the point PM associated to the subpixel M, which can be found from PB given unknown displacements dx, dy, and dz. We then make use of an orthogonality constraint in camera coordinates, enforcing that the displacement vectors are perpendicular to the surface both at the point PB and at the point PA. Finally, we model a discontinuity epsilon at the subpixel location M. Solving the resulting system of equations for the displacement vectors yields the following relation between the depth values at the neighboring pixels. Importantly, the two coefficients depend on dot products between normals and ray direction vectors. We note that these dot products are known quantities in the literature. In particular, a strict condition for a surface point to be visible along a given ray is that this dot product is negative. Points on the surface boundaries have null dot product, while points that have a positive one are occluded. From the derived condition, we express the discontinuity in relative terms, rearrange, and take the logarithm of both sides using the positivity of the multiplicative factor. This way, we obtain an additive relation in log space between the depth at neighboring pixels. This relation takes the same form as the previous formulation based on partial differential equations, but with different coefficients and properties. In particular, it explicitly models discontinuities, handles generic central cameras through the ray direction parameterization, and as we find in our experiments, more accurately models the ground truth relation between depth and surface normals. To use our derived formulation to integrate normals in an input normal map, we enforce it for all pairs of neighboring pixels. These constraints can then be rearranged in matrix form. Similarly to previous methods, we solve for the unknown log depth values through an iterative least squares optimization problem. We use the bilateral weighting scheme from the previous method BINI, which at every optimization iteration compares the log depth differences on the two opposite sides of each pixel. If this difference is significantly larger on one side than on the opposite one, the equation for the more continuous side receives a weight close to 1, while the equation for the less continuous one receives a weight close to 0. An important aspect is that the discontinuities modeled by our formulation are not known a priori. While optimization can be run without modeling discontinuities, like previous methods, we propose a strategy to iteratively incorporate them throughout the optimization. In particular, we initialize the relative discontinuities to 0 and parameterize them as the product of two terms. The first term is derived based on the current reconstruction by inverting our formulation, while the second term intuitively prioritizes the computation of alphas for the equations that are more likely to correspond to a discontinuity and therefore benefit from a correction. We evaluate our method on the standard diligent benchmark. Our formulation results in more accurate reconstruction also without discontinuity incorporation. However, modeling discontinuities further improves results. Our method is effective particularly for objects that contain larger discontinuities, as can be seen in these visualizations. For each object, we show the output reconstruction on the left side and the mean average depth error on the right side. Through its parameterization based on ray direction vectors, our methods can be applied to normal maps from generic central cameras. Here we show the case of cameras with Brown-Conradi distortion. For illustration purposes, we also show the output of Beanie for such a normal map. Since Beanie does not model non-ideal pinhole cameras, its output reconstruction shows distortions, unlike our method. Undistorting the input normal map allows removing these artifacts, but at the cost of reduced field of view. Thanks for watching.